In this video, we'll talk about the meaning of the central limit theorem. The central limit theorem actually says a couple of things. One thing it says is that if the population is skewed, then the sampling distribution will be skewed just like the population when the sample size is small, meaning less than 30, and the sampling distribution will be roughly normal if the sample size is large, meaning at least 30, 30 or higher. And we're going to look at a little bit of a demonstration of the idea of the central limit theorem. This is supposed to be a picture of the university, Cal State East Bay, with all of the buildings, and we're just imagining that these are the different students in the population. Obviously, there would be many more students in the population than what I'm showing here, but this is just meant to demonstrate the idea of the central limit theorem. So we're saying that each of these stick figures is a certain student at Cal State East Bay. It's a certain population number, and the number above that student is the student's height. So here we have a student who's 50 inches tall. Here we have a student who's 50 inches tall. Here we have a student who's 63 inches tall. And we're imagining that most of the students at Cal State East Bay are shorter students, and that there are fewer taller students in the population. So we're imagining that the heights of the Cal State East Bay population are positively skewed, following this type of a curve right here. And what if the heights of the population are positively skewed like they are here, and I take a small sample of 4 students from the population, I record their heights, and I calculate the mean of my sample. These 4 people in my sample have a mean of 51 inches. So if I recorded the heights of these 4 people and calculated the mean of these 4 people, the mean would come out to 51. Because if you add these 4 numbers and divide by 4, it comes out to 51. So the mean of my selected sample would be under this curve right here, and it would be right here. That's about 51. So this is the mean of my this is the mean height of my sample of 4 people that I've selected. And under this curve is the means of all possible samples of 4 people that I could have selected from this population. So what if I select a different sample of 4 people? What if I select this person right here? This person right here. Maybe this person over here. And just to show you that the samples can overlap, maybe I select this person over here a second time. And I record the heights of these 4 people in my sample in the green circles. So I've recorded these 4 heights in the green circles, and if I calculate the mean of my sample of 4 people, the mean of this sample will also come out to 50, because these if you add the heights of these 4 people in the green circles and you divide the total by 4, the sample mean comes out to 50. Actually, that's not correct. It comes out to 51. It comes out to 51 just like my first sample. So now I've selected a second sample that also has a mean of 51, which would mean that the blue sample and the green sample both have means of 51. So these two x's would be on top of each other. This right here, this x is the mean of one group of people that has a mean of 51. And this right here is the mean of a different group of people that also has a mean of 51. One of these is the blue sample, one of them is the green sample. Now I go out and I select a third group of Cal State East Bay students to be my sample, and I record their heights. What if this time I get this one, this one, this one, and maybe this person right here who has a mean of 50. The 4 people in orange are my third selected sample. Let's find out what the mean of this sample would equal. It would be 50 plus 52 plus 52 plus 63 divided by 4. The mean of my third sample equals 54.25. So the mean of my third sample would be about right here. So the first 2 samples both had a mean of 51. Those 2 samples are both right here. My third sample was a little bit taller. The third sample had a higher average, so the third sample is right here. They're further to the right. They're further to the right in the sampling distribution. And what we're starting to see is that a lot of since the population is positively skewed and there's a lot of shorter students in the population, there's a lot of possible samples of 4 people that have low averages, because if the population is skewed and there's a lot of shorter students in the population, then there's going to be a lot of possible groups of 4 people that are shorter groups of people who have low averages. Like here's one sample that had a low average. Here's one sample that had a low average. Here's another sample that had a low average, and they're all piling up in this left end of the sampling distribution. So if the population is skewed like this, and there's a lot of shorter students, then a lot of the possible samples of 4 people will include shorter students, and a lot of the possible samples will have low averages. There aren't as many possible samples out there that will give me the high averages out here. Now, even if the population is positively skewed, it is possible to have a sample with a high average, because what about this possible sample right here? 75, 79 inches, 70 inches, and 67 inches. This is another possible sample of 4 people, and let's see what their mean equals. 67 plus 70 plus 75 plus 79 equals 291 divided by 4. They have a mean of, this group of 4 people has a mean of 72.75. So their sample mean is out here. So this is a tall group of 4 Cal State East Bay students. Each of these samples that I've looked at is a different possible sample of 4 students who could be selected. 3 of those samples had low means, and one sample had a high mean. But the idea is, if there's a lot of short students in the population, most of these possible samples that are out there will have low averages, and fewer of those possible samples will have high averages, like this sample right here. But that's actually only true with a small sample size, like a sample size of 4. What if I took a big sample from the population, such as a sample of 30? I'll clear off this right here. So I'll select 30 people in a certain color. So right here in red, I've selected a sample of 30 Cal State East Bay students, and we're imagining that I'm recording their heights. If I calculated the mean of my sample, meaning I added their 30 heights and divided by 30, the sample mean will probably be actually somewhere in the middle right here, because we can see that there are a lot of shorter students in this sample. And it makes sense that there's a lot of shorter students because there's a lot of shorter students in the population. But because it's a big sample size, there's also a lot of taller students mixed in, like these students right here, or these students right here. Those people bring up the average of the sample, which means that the sample mean is probably going to be somewhere in the center, right here. And under this curve right here, we have the means of all possible samples of 30 people that I could select from the population, including my one selected sample right here. Now, if I went out and selected a different group of 30 students from the population and calculated their mean would also probably fall somewhere in the center of this curve. Because once again, there's probably going to be taller students mixed in who bring up the average. So even if the population is skewed with a lot of shorter students in the population, the means of the different possible groups of 30 people that could be selected are actually roughly bell-shaped, because if I'm taking a sample of 30 from the population, there's a lot of possible samples out there that have medium averages. And there are fewer samples out there that have low averages, and fewer samples out there that have high averages, because the larger sample size helps balance things out. Now we've covered the first half of the central limit theorem, which says that if the population is skewed, then the sampling distribution will be skewed just like the population with a small sample size, but will be roughly normal with a large sample size of 30 or higher. This is the second half of the central limit theorem, which says that if the population is normal, then the sampling distribution will be normal no matter what the sample size is. So now let's imagine that the heights of Cal State East Bay students follow a normal distribution, meaning most of the students have heights in the middle, and there's fewer shorter students and fewer taller students in the population. And let's also imagine again that I select a sample of 4 students to be my sample, and I calculate the mean of my sample. Let's see what this sample mean comes out to. If I record these 4 heights and I add them and divide by 4, divided by 4, the mean is 58, which is it's actually a pretty low average, so it's probably going to be out here somewhere. So if the population is normal, like this, it is possible for me to select 4 shorter students and to have a sample mean that falls out here somewhere. But since most of the population members are in the middle right here, I'm usually, if I select a sample of 4 people from this population, I'm probably going to get 4 students from the middle who have medium heights, and the sample mean will come out somewhere in the middle. So if the population is normal, like it is here, and I'm taking a small sample, then most of the possible samples that are out there will have medium averages. Um, even though the sample size is small, most of the possible samples that are out there will have medium averages because the population members have mostly medium heights. So the central limit theorem also says that if the population is normal, the sampling distribution will be normal even with a small sample size. Imagine this. If I kept on selecting more and more samples of 4 people from this population and calculated the mean of each one, most of the samples that I end up selecting will have sample means in here in the middle. I'll probably end up getting fewer samples that are especially short with low averages. And I'll probably get fewer especially tall samples with especially high averages. And if I'm taking a large sample of 30 and I'm calculating the mean of my sample, the sample mean will once again probably be somewhere in the middle in here. So overall, if the population is normal and most of the people are in the middle, and you're taking a small sample from the population, most of the possible samples that are out there will have medium averages in here. All those samples are in here, and fewer of the possible samples will have low averages, and fewer of the possible samples will have high averages. And you have this normal curve. If you're taking a large sample of 30 from the population, most of the possible samples will have medium averages. Fewer of them will have really low averages out here. Fewer of them will have really high averages out here.